Hi, so this is our group video project over thermodynamics and equilibrium. I'm Ava Violet.
I'm Morgan Thompson.
And I'm Jada Flitton.
I will be going I will be going over the solubility product. The solubility product, KSP, represents a solubility and equilibrium constant for a solid substance that dissolves in an aqueous solution. The higher the KSP value, the more soluble the substance is. This is important in chemistry because it can help predict the extent a solid substance will dissolve. With this, we can measure how much of a soluble ionic compound can dissolve in water, which is critical for the prediction of precipitation reactions. A way KSP can be implemented is in quantitative analysis. The solubility product calculates molar solubility. This helps determine the exact amount of substance needed to dissolve under specific conditions for more precise measurements, which is crucial for quantitative analysis.
I will be going over thermodynamics and equilibrium. So, thermodynamics is about understanding how energy moves around in a system and how that energy flow dictates whether a reaction will actually happen. It also tells us the conditions under which a reaction reaches equilibrium, which is the point where the forward and reverse processes balance out. Down here we have the thermodynamics constants, which is delta H, which explains how heat is absorbed or released during a reaction, delta S, which is the measure of change in randomness of the system, delta G, which is the driving force, and determines if a reaction is spontaneous or non-spontaneous, which is whether it will occur or not. Now, the reason all of this matters for equilibrium, especially for something like KSP, is because solubility is strongly influenced by energy and temperature. If dissolving a salt requires or releases heat, that will directly affect how much of it can dissolve at different temperatures. Using delta H, delta S, and delta G lets us predict these trends and determine whether dissolution is favored or not. So thermodynamics is essentially the toolkit that lets us understand and even forecast how equilibrium will shift.
Moving on to the experimental data and results. Looking just on trial and sample one, we can see the calculation for moles of potassium nitrate, which comes out to about 0.1978 moles. In addition, we have the mass of water from that was calculated within the lab. And then the molality, using those two constants, we ended up finding the molality from that, which allowed us to overall find the delta G that came out to be about negative 15.23 kilojoules per mole. Over to the right, there is a plot of this that demonstrates the natural log of KSP versus 1 over temperature in Kelvin. Um, we expected it to form a straight line based off of the Van't Hoff equation. And I think it's really important to point out that the slope of this plot is going to equal negative delta H over R. And a negative slope basically indicates that delta H is positive, meaning that the dissolution of potassium nitrate is going to be an endothermic process. Looking towards the y-intercept with that 19.22, that's going to correspond to the delta S over R, which basically talks about how the entropy change when the solid is dissolved. And so overall, the straight line behavior uh, allows us to understand that the system follows the Van't Hoff relationship, and then the plot allows us to determine the enthalpy and entropy changes for the dissolution process. Moving on to talk about the determination of delta H and delta S, and relating back to what I said previously on the slide, we can see how the Van't Hoff equation corresponds to our typical understanding of a line with y equals mx plus b. And then towards the bottom of the screen, we can see how the slope does indeed correlate to the negative delta H over R, and the y-intercept, which is represented by b, correlates to the delta S over R, and the calculations through that given what we got from the plot. Um, and so from that, we can see that the slope was about negative 4,829.3, and the intercept was about 19.22. And then from that, we can understand that The enthalpy change of delta H was about 40.15 kilojoules per mole, which tells us that the dissolution is endothermic, meaning that it will absorb heat throughout the experiment. And then relating this to delta S came out to be about 159.9 joules per mole Kelvin, showing that the system becomes more disordered when potassium nitrate is dissolved. So overall, these values describe how the temperature is going to affect solubility and give us a greater insight into what drives the dissolution process. Thank you.
Thank you.
Thank you.